Hello students, this is lecture number 23 and we are into the chapter number 6. Okay, so as we discussed in the last video lecture, today we are going to start with Green's theorem, and we will also talk about the divergence theorem. Green's theorem is about the gradient. Okay, so this is about the gradient, and this tells that if, let us say, a domain is something like this one, and this boundary is given by gamma, domain is given by omega, then anything p, let us say p is defined over this domain, okay, which has boundary as gamma, then gradient of p, okay, d omega is nothing but, it tells this will be equal to is equal to n or p n d gamma or integrated over the whole gamma. So, where p is a scalar, p a scalar quantity defined over yeah, okay. So, this is what the Green's theorem is, and the divergence theorem, on the other hand, this is about divergence, and this tells that divergence of vector p, okay, and that will be equal to p dot n integrated over the whole boundary. So, here p is a vector defined over omega. So, this has to be integrated over the whole boundary, hence this is like closed integral, yeah, so like this. Okay. Now, this is what you study during engineering mathematics during your BTech, and here we are just making use of it. However, it has some physical meaning. So, what it tells that in both the cases what you have is some differential, basically, right? The slope of p, somehow it is related, right? So, here, although this in the form of divergence, in this case in the form of gradient. So, what is the meaning of that? So, let us try to understand in case of one dimension, what is the meaning of those. So, in one dimension, as we say, like let us say domain is like this, linear domain it is, right, okay, and here omega, like when you say omega, that really means x goes from say x equal to 0 to x equal to L. So, omega is basically x, where x is less than equal to L, right. So, this is, so you can say x is less than L and x is greater than 0. So, this is what your omega is. On the other hand, when you say gamma, gamma here means x equal to 0 is one gamma, and x equal to L is another gamma. So, this is gamma 1, you can say this is gamma 1, this is gamma 2. Okay. Now, let us look at what is the meaning of the Green's theorem in this case. So, Green's theorem. Yeah. So, Green's theorem, what so basically this is it says omega, and then you have gradient of p, right, gradient of p, and this one, and we call it, this will be equal to yeah, closed integral of p n. So, basically we can put n, you replace this delta with n, that is it. So, p n basically that d. Okay. So, in 1D that really means if you have 0 to L, yeah, and some gradient, right, some gradient of some p dx. Yeah. So, in this case gradient is nothing but is we are talking about del over del x only. So, 0 to L dx, sorry, d, the meaning of del in this case is nothing but d over dx I only, right. This is what the meaning of that, multiplied by p dx is equal to 0 to L I for the unit vector in the direction of positive x. So, you have I, unit vector I, and then dp over dx, okay, done. And you know that will be, that is equal to we have I and then 0 to L, and then x cancels out. So, you have dp basically simply. So, but not here. So, we write not 0 and L, but we have to write here dp and p at L and p at 0. So, we write here p at L and p at 0, and what you get is I and then p at L minus p at 0, right. Okay. This is what your answer you get, and this is equal to p L. Okay, maybe on the next page. So, we have this answer. Yeah. So, what do we get? So, in one dimension the answer we get is p, this is I, and then p at L minus p at 0, okay, and this is equal to p at L I plus p at 0 at minus I. Okay, so basically what we see, the value what you are getting is something like this. So this is P at L, and here this is a vector which is I vector, and then we have P at 0, actually the value of P at the boundary, value of P at the boundary, and then this is we have minus I, right. So what we did, so basically here the integral over the whole thing, it looks like you don't need to know. What you need to know is just what's the value of P at L, what is the value of P at 0, and then multiply by the normal vector at these sections. Yeah. So normal vector here is I. So in this case the boundary, perpendicular to the boundary, you have one unit vector which is I. In this case, since area is like this one, so outward unit vector is minus I. So you just write this multiplied by this plus this multiplied by this, and you get the answer. That's what is the meaning, right? Or simply what you got is this one is, you can also in one dimensional you can write this as you are actually done this P and N. So you know at this point N is equal to I, at this point N is equal to minus I. Yeah. So this has completed, right. So since it has only two boundaries, hence you have P this will be equal to only two things, one this boundary plus this boundary. At this boundary P is PL, N is I, so you write PL times I. At this boundary you have P naught, so you have P naught multiplied by N, but at this boundary value of N is minus I, hence you write minus I, so totally you get this one. Hence this is what the meaning of the Green's theorem. So the Green's theorems we have done here in one dimension. Okay, similarly if you want to, you can extend that to basically the 2D. Yeah, so 2D, in 2D you can assume that, say 2D is like this one. Now you can have one strip here, right. So you can have one, so this one is, just think about one strip. This one strip will look like something like this. So we are talking about, so for this one we have we can say this is omega 1, and we can say this one is gamma 1. So we are talking about the number 1 strip. Yeah. Okay, so that really means that if we have some P which is defined over the whole domain, yeah, and so we can gradient of P over the whole domain will be equal to, we can have something like this, summation of, yeah, we will have summation of this omega defined over dp d omega I, right. So this is a, so we can sum it like this one, 1 to n, the number of strips that we are making to complete this one. Yeah, so what we will get is, for just for one we know that we get this kind of thing, right. So what do we get? We get something like this. Yeah, okay. So we know that for 2D we are converting into just 1D. So we will get whatever the value of n here. So let's say this is value here like this, value here is like this one. Yeah, and let's call this is n 1 2, this is n 1 1. Yeah, okay. And then there will be value of p also here. Okay, so we can say p 1, p 1 1 here. Yeah, so basically what we get here is a summation of I equal to 1 to n, and we will have this, whatever the value we have at the boundary, we are going to add that. We know that when we, for this is 2D, we have converted into 1D, and we know that this gradient, when we integrate, depends on the value at the end only. Hence we see here this will be equal to basically I equal to 1 to n, and we can write this way. Yeah, so basically we have p. Okay, so p, the value of p here, so let's call it p gamma 1 1. Okay, so this let's call it gamma 1 1 and gamma 1 2. So the gamma 1 1, sorry, gamma 1 2 here, and this is gamma 1 1 here. So this is the first end, the second end of the first. Okay, so okay, write ith one. This is ith one. Okay, this is ith one. So ith strip. Okay, so this ith strip, and we have the first boundary and second boundary here. So we are writing like this one. So we get p, we write like this one only. Okay, so we have p at p at the first boundary. So p at the first boundary, so gamma I1 and then n. So let's call this one ni1 and ni2. Okay, so we have n I1, okay, then plus we have to add this also. So will be p gamma I2 plus n I2 as well. Yeah, and then this is for n, for all the strips we will do like this one. Okay, so basically the idea is to just to show you that finally what we will see, that the whole thing, the whole domain is being converted into just finding what is the value here only. Yeah, and also like this one, this is about so we have gradient multiplied by area, if you see. So in this case, if you say the gradient multiplied by area, so finally the dimension should be p times length, right. So this is p P per unit length multiplied by area. So, P times length. So, similarly here we have P, there has to be some length there. Yeah. So, we have to multiply by whatever the length of that is. So, let us say the length there is we can say this length is L, right. So, we have L1, Li1, and this is Li2. So, similarly we need to multiply with. So, here we have Li1 and here okay, here we have to multiply it by Li2. Okay, this is not plus, remember this is this one is multiplication basically. Okay. So, basically what we get if you look at that is we are going to add for the all strips together, and you can find out finally what it works is what is the value of P here, then what is the value of unit vector perpendicular to this this boundary multiplied by length of this, yeah, and we are going to sum them up. At every point we are going to do the same thing. Okay. So, basically we are summing up what? We are summing up P, the value of P at the boundary multiplied by what is the unit vector at that boundary, and we are doing for the whole boundary. So, basically what we wrote here is actually the same thing. So, we can basically write that this tells you is nothing but basically same thing. Yeah. So, this means this. So, we just understood. Yeah. So, you just if you know if you understood the 1D like Green's theorem, yeah, so we can apply that to in 2D as well, and hence this will be equal to this that you see physically. The idea here is not to do the mathematics. Here the idea is to understand basically we get the insight what is the meaning of that. Yeah. So, this is the insight. Now, next is the divergence theorem. Okay. And this in 1D, if you look at that, then what is the meaning of that? So, it says this. So, we have divergence of P and d omega will be equal to, we have P dot n like this. Okay. So, in 1D what is the meaning? If you understand in 1D, you will understand. So, let us do what is the meaning of that. So, let us say you have something, the again this is the 2D, and you have a P vector which is the P vector like this one, P vector here defined, yeah, and then so this in 1D means simply d over dx I, yeah, and P vector will be equal to, let us call P equal to Q, which is a or let us say this is yeah, okay, Q is fine. So, Q is a constant, this is a scalar quantity. Okay. So, please do not think this is flux. Okay. So, this is a scalar quantity. Okay. So, Q times I. Okay. So, if this is this will be the in 1D, this is how the P will be defined. Q is scalar, can be negative as well. Yeah, so like this one. Now, what it says? It says the gradient divergence. So, divergence means this dot this one, and hence this simply says d over dxi and dot qi, and then this means dq over dx simply, and there is no this becomes a scalar. Okay, so gradient of this the divergence itself is a scalar quantity. Okay. Okay, now if we integrate this one, what is the meaning of that? So let's see. So we are divergence of P d omega, omega will be equal to 0 to L, and we have dq over dx, and dx will be equal to simply what we see here is 0, and then we have now q you see, right, so not 0 but q at 0 and q at L, yeah, okay, and then we have dq, and what we get simply is dql minus q naught. So this is the answer. Okay. Does it here we got there is no n, nothing, so we just have this minus whatever the value of this q is here minus whatever the value of q here, we just subtract it and we get that. Okay, so looking at this one, if we have, we can extend, and this actually is no, in 1D it's fine, right. So what we look at this one is, it says like this, if you want to integrate dq over dx, you don't need to see what is the value of this, not even you don't need to even integrate, you just see what is the value of q here and what is the value of q here, subtract this from this, that's you are done, and what you find out, the integration of gradient of the gradient of q, the slope of q, or the divergence of p. So divergence of p is nothing but the value of q here minus value of q here, and this makes sense. The statement wise also you can see what is the meaning of here. Here it is telling you that you just evaluate what is the value of, you add the value of p dot n at these boundaries, that's it. Yeah, so what do you have to do is whatever the value of p is here dot n. So we know that the value of n here, the value of p here is, so p here will be some q l, right, I l, this is what that is, and n here will be equal to, n will be equal to simply I. On the other hand, p here will be equal to q at 0, right, q at 0 and q at 0 at like this. Okay, and what is the value of n? N is basically like this, n is equal to minus I, is what that is. So QL you will get y by p dot n, you get just QL, and how will get q naught? Qn, you say p which is equal to this dot n, you will get minus q naught. So, minus q naught. So, basically what you are getting, this one is nothing but this only, simply, right. So, it follows in 1D, it is actually following the same thing. You can give the same argument as you have given here, like you can divide the whole 2D into these strips, and finally you can actually do the same logic how you got the same thing, right. So, basically what it means is, let us say you have 2D domain. So, let us ith strip we are talking about, yeah, and we can have the same kind of equal omega I, and it will have two boundaries. Let us say gamma, this is gamma I 1, gamma I 2, two boundaries. Okay. So, what it is talking about is this one 0 to this omega gradient as a divergence of p will be, we can write as a summation I equal to 1 to n summation of what? Summation of this. Yeah. So, total area, the integration over the whole area is equal to some integration over this strip, and repeat that for all the strips basically. So, this is how it will be, but if you take only one, so where this okay will be equal to simply whatever the value of q here, right. So, whatever value of q here, so will be simply q at gamma I 2, right. Okay. So, q at gamma I 2, and but what is q? So, or we can write like this one. So, this is nothing but the p dot n at gamma equal to gamma I 2 plus p dot n at gamma equal to gamma I 1. Yeah. Okay, and we also have to multiply by the length, how long it is, because this will be integrated over the, this is 2D basically. So, gradient multiplied by area, sorry, the divergence multiplied by area, or slope multiplied by area. So, this is the whole thing is some quantity per unit volume, per unit length, and then multiplied by area. So, this quantity multiplied by length. So, hence length you have to multiply here. So, let us say length here was L I 1, this is L I, this is L I 2. Yeah. Okay. So, this so you get this, you multiplied by L I Li2 here and then Li1 here. Okay. Okay. So, and this is what just for ith strip, and hence you can extend that for this divergence of P d omega will be summation I equal to 1 to n and then Li2 gamma equal to gamma I2 plus equal to 1 to n Li2 P dot n gamma equal to gamma I1. Yeah. Okay. So, this is that really means that finally it depends on what is the value of p vector dot n vector at boundaries multiplied by those length of that boundary, and this has to be integrated over the whole boundary. That is what it is telling you, and hence we can write simply, meaning that the closed integral and then you have the whole gamma and we have p dot n d omega. So, with this exercise we actually now understand just the meaning of the divergence theorem. Okay. So, and this we have applied already to obtain the weak formulation for the 2D heat transfer problem.